All right, thank you, Lev, for having me as part of this workshop. I'm going to be doing something a little bit different. Okay, so why is there no consensus on many worlds interpretation? It seems favored on explanatory grounds, right? As we've seen earlier, different interpretations of quantum mechanics have different advantages and disadvantages. But according to a recent survey, only 6% of physicists support the many worlds interpretation. Why? Well, there's one big worry, which is that other worlds are unobservable and hence purely speculative. Sound science, many think, requires empirical confirmation and or disconfirmation, falsifiability. There's a more general problem for interpretations of quantum mechanics, which is the problem of underdetermination of theory by evidence. There are always, in principle, an infinite number of theories consistent with the same empirical evidence. And in this case, we've got multiple theories that are consistent with the same quantum evidence. And so the empirical evidence doesn't seem to favor any one over the others. So how to move towards consensus? I'm going to pursue a peculiar possibility. I'm first going to show that some interpretation of many worlds interpretation explains something important using observable phenomena that no other interpretation of quantum mechanics does, not even the traditional many worlds interpretation. Namely, it's going to explain why our world is quantum mechanical to begin with, in terms of observable mechanisms that comprise many worlds. Second, I'm going to show briefly that this new interpretation of the many worlds interpretation makes some novel predictions. So there are two explanatory questions in physics, or in any theory, right? Existing interpretations of quantum mechanics take quantum phenomena as given, that is, as fundamental laws of nature. They then aim to explain the epistemic and ontological import of those laws. So the Copenhagen interpretation gives one explanation of what is going on in quantum mechanics, many worlds interpretation, another explanation about what is going on. So they answer the what question, or at least they purport to, what quantum mechanics is. Many worlds, right? Superposition. Yet none of them answer the why question, why our world has quantum characteristics in the first place. Why not a single determinate reality instead of, for example, many worlds? Why does our world have these strange quantum features? Now, in several articles, I argue that computer networking explains quantum superposition, indeterminacy, wave-particle duality, wave-function collapse, entanglement, and in principle, minimum space-time length, because as we'll see, computer networking uses distinct packets of information that have a minimum length that's possible to understand within a simulation. Now, the simulation hypothesis, going back to Bostrom, is regarded by most as highly speculative, but I argue that a particular version of it has immense explanatory power, explaining why our world is quantum mechanical to begin with and why it is comprised by many worlds. This computer scientist programmer, Eric Grange, has argued that, in fact, a mesh world version of this thesis in computer networking uses adaptive partition mesh networking, can also, in principle, explain why there's a maximum speed limit in our world, the speed of light. Okay, so in computer networking or in simulations, video games, there are two different types of ways of designing the game. One type of simulation is called a dedicated server simulation. Okay, so in this case, there's a single dedicated server that has a definitive record of where every single player is in the game, where every object is located in the game, what direction the players are facing, the physics of that reality. It's determinately settled by the dedicated server. Now, one problem with dedicated servers is that they crash, right? Sometimes the game will end because the dedicated server will have an error and everyone dies. So another approach that prevents crashing is called a peer-to-peer network. This is also used in blockchain technology and cryptocurrency. In a peer-to-peer network, there is no definitive computer that represents where everything in the game is located. Instead, every single computer, every player has their own world, representing where players are in the game, the activity, the player interactions, where objects are located in their environment. And the physics that's happening around each player and the score and rules. There is no definitive record anywhere in a peer-to-peer simulation about where objects are located, what their velocity is, and so on and so forth. So, a P2P simulation simply is many worlds, right? So I've given some examples of worlds here. And the player and the bullet or the object is located in slightly different positions in each version of the game. they're communicating with each other, with all of each other in real time, receiving inputs from every other node and sending inputs to every other node, okay? So I've given you here 9 players, but in a massive peer-to-peer game like some video games today, there'd be millions of players playing simultaneously, their computers networking with each other, updating in real time, right? And so if our reality is a peer-to-peer simulation, then there's at least 7.753 billion players on Earth alone, and of course we're in a much larger universe than that. Okay, so the interesting thing about a peer-to-peer simulation is that if you sum over all of the individual nodes that represent where an object is in their local contextual environment, you get a superposition, right? The simulation summing across all nodes simply is a massive superposition of where players are located, where bullets and other objects are located, their direction, velocity, and so on. Okay, so now, for reasons we'll talk about shortly, computers on a peer-to-peer simulation do not all represent objects as being in the same place. Errors emerge in real-time networking, right? So in this case, we've got 3 computers indicated in red, representing a bullet being in a particular location, 1210 on the XY axis. We've got 1 computer in blue in the center, representing it being at the 1010 XY axis, and so on and so forth. So if we want to ask the probability that a particular player will observe the bullet in a particular location, we have a probability distribution. That is to say, an amplitude equivalent to the number of game consoles that represent the object in that location. And this probability distribution, these amplitudes, will change over time as the computers communicate with one another. And of course, a changing amplitude over time is, of course, simply a wave function. Now, why do these errors occur? Well, in networking, there's 3 sources of errors where computers can represent things in different locations. One is latency. It takes time for one computer to communicate with another. And all of the computers are doing this in real time with one another. So there's a delay in communication, and yet each computer has to render where an object is for its local user, for the player that's playing the game. Now, in addition to that, right, in addition to the natural latency or time it takes for one computer to communicate with another over a network, there's also something that many gamers would recognize called lag. This is when there's a further delay in information between computers that can result from a congested computer network, from too much information flowing through the network at the same time, can delay information further. And then finally, there's what's called packet loss. Sometimes computers simply don't receive information from another computer. It gets lost for one reason or another in communication in the network. And we know that informational variance in these types of cases, as in many types of cases, tend to fall naturally upon a normal distribution. And this can change dynamically according to, for instance, lag, right? So lag can change over time, given the quality of the networking at that time. So how do peer-to-peer networkers handle these problems of different computers representing objects in slightly different places? They want to provide users with a believable environment so that they see a person in approximately the same spot as anybody else on playing the game. Well, they do so via a programming technique familiar from aeronautics called dead reckoning. So in this case on the left, we're using deduced reckoning. We're deducing where a particular airplane is going to be at time 10 o'clock from its velocity and direction at time 9 o'clock. It's a very simple case of linear dead reckoning. And so what computer programmers do is they try to extrapolate where a player is likely to be given their velocity and direction at the same time. Then they update it with a new dead reckoned velocity and direction at a later time based upon the information that they get from other nodes. Now, what happens, of course, in aeronautics is that you have drift. So you don't use simple linear dead reckoning, right? Airplanes drift off course due to winds, right? They also drift off of a consistent velocity due to headwinds and tailwinds and variances in their engine power. And so what dead reckoning does is it has us correct for variances, right, by calculating the angle to bring the airplane back where we want it to be. game designers do exactly the same thing in a three-dimensional environment. They try to extrapolate where a player or object in the simulation should be, given other data that they get from other nodes, which again is not exactly the same as the data that this particular node is plotting at that particular time. Now, what's interesting is that if you correct for random drift in 2D, you have alternating, right, angles of correction. You want to correct upwards and you want to correct downwards for equal drift, right? And notice that this approximates, at least in a triangular shape, the shape of a wave, right? So you've got wavelengths and amplitudes. In this case, you have these sharp angles. Now, game developers don't actually use sharp angles because if they did, you would have jagged movements in the game. So what do they do instead? Well, they apply, through dead reckoning, certain types of curves from mathematics. Bezier curves, centripetal Catmull-Ram spleens, and Hermite curves to handle or to make the plotted expected location and velocity of any object to appear smooth to their users. So let me talk a little bit more about how this works. Okay. Now, one interesting thing is it's been derived mathematically that the optimum cubic Catmull-Ram spleen interpolation function, right, that works the most efficiently has the shape there on the left, which should look very familiar to many of you, because if you extrapolate that very shape into 3 dimensions, you have what is, in essence, the wave shape of an electromagnetic wave in our reality, which is interesting. So it looks like we're going to get something like EM waves directly out of computer networking using dead reckoning in a peer-to-peer environment and using certain types of curves. Okay. All right, next. So when computers come apart, they not only use curves, but they want to correct for errors. And how do they do it? Using dead reckoning. There are multiple approaches, but 2 very common ones used are what are called projective path blending and predictive velocity blending. And they do these things using neural networks of various depths. The very short story is an object's eigenstate, right, is basically selected on any node by a predictive averaging of all of the information that they get from other nodes. So an average of the object's location as represented in the other nodes that's sending them information in real time, okay, and vice versa, okay. Now, when we pursue dead reckoning without predictive path blending, and then also blending the velocities that one is getting from different computers, which are slightly different again, if you do dead reckoning without predictive blending, then macro objects do not have a believable path. So the object will be tracing a perfectly circular path in one user's experience. But if you do not use predictive path blending and velocity blending in dead reckoning, what you get is on another computer, right, that object not moving in a circle, but having undulations, right, or oscillations, which is not believable, right? It would not look believable to a user. But when we apply projective path blending and velocity blending to macro objects, those oscillations disappear on a macro level. So the object appears to take a believable circular path macroscopically. Okay. So the oscillations are not visible or hardly visible at a macroscopic level when using computer networking in this way. Okay. Now, another interesting thing about peer-to-peer networking is that they use packets of information, well-defined packets, which have, on the one hand, a macro structure. So any particular packet is a particular full length of information, but always also contains microstructures, right, designating properties such as velocity or location and so on and so forth. Now, insofar as computer networking uses determinate packets, this means that there will, in any simulated environment, be a minimum space-time distance below which space and time make no sense, which is, of course, roughly what the Planck length demonstrates is the case in our world. Now, in addition, because errors will occur, right, both at the level of the macrostructure and within the microstructures as well, in terms of what computers are sending to one another, then in any peer-to-peer network, there should be a dominant wave packet associated with any information that is constituted by waves, in this case, micro ripples, which of course is what we find in Gaussian waves in quantum mechanics. All right. Now, how can we understand things like the double slit experiment in dead reckoning and peer-to-peer networking? Well, one interesting thing is in order to ensure a believable environment so that there isn't slowdown, for example, where because of processing limitations, the environment would appear to slow down from users. You don't want that. So what peer-to-peer games do is they only render the environment within or surrounding the player's point of view. Okay? And as the point of view changes, new areas are rendered and then new areas are unrendered. There is no location determinant for those objects on that particular game. Okay. So, as we're going to see in the next slide, there's also something called partial rendering that is used in game networking, where you represent only part of the player's point of view, namely the macro point of view, not the micro point of view. And this is also used to reduce complexity, to make sure that the game runs well, right? So if we think to begin with about the double slit experiment, the individual paths, right, that multiple computers are sending you about where the particle is likely to be are not going to be rendered by your computer because it would cost too much computational energy on your computer's processor. So those will not be rendered. This is how this works in actual video games, right? So if you're a player going about an environment and then you look through your little scope there, then more details at a micro level will be rendered that were never rendered to begin with. Okay, so they become rendered as you zoom in, like you zoom in on microscopic objects in our world. All right, so how is a peer-to-peer simulation going to handle the sheer amount of complexity, the number of particles that are in principle occurring and have paths at a microscopic level? Well, to save computational resources, you're not going to render on any given computer exactly where those particles are located, unless you set up a set up a detector. Okay. The moment you bring the object into view microscopically, just as we saw before, it's at that point that the object will be rendered as having a determinate location or eigenstate. And so this explains in principle why when we do not have a detector set up in the double slit experiment, we get a wave pattern. But when we do zoom in and detect where the particle is, it always goes through one slit and behaves like a single determinate particle. Okay. Now, I skipped over this. So the interesting thing is that different computers on the network will adopt the same approach, not rendering where the object exactly is, but instead rendering the dead reckoning solution, which again is a waveform. But because there are errors, again, between nodes, different computers will represent the wavelengths themselves as being in somewhat different places. And so when they communicate via predictive path blending and velocity blending, when you blend a waveform, what do you get? Well, when the waves overlap, you get constructive interference. When they overlap in the wrong way, you get destructive interference, which simply is a kind of path averaging between multiple waves. So we get it through peer-to-peer networking, the result that we should have a wave pattern in a double slit experiment until we set up a detector. Okay. So why believe in many worlds? Well, suppose our world were like a clock, and we lived on the surface of the clock, and we saw the hands moving around in front of us, above our heads, and we wanted to understand what's going on. Now, what physicists would do is they would measure and develop the laws that govern the minute hand, the hour hand, and the second hand. And if we wanted to set up clock accelerators, we might accelerate the hands to see what happens, much as we do in particle accelerators. But all that would do is tell us how the hands are behaving, right? Not why they're behaving in that particular fashion. Right? The real explanation about why the hands behave in that way is below the surface of the clock, that we cannot directly observe. Okay. But of course we know, right, what's going on beneath the surface of a watch or beneath the surface of a clock like this. There are gears, and those gears are the deeper explanation about what's going on and why the hands are turning the way that they do, right? So if our world behaves just like a clock, then the best explanation is that it too has many gears that are causing the hands to turn in that particular way. This is not beyond empirical confirmation. It is a sort of empirical confirmation by abduction from phenomena that we have very much observed before, how clocks work. But now if this analysis is correct, it also explains, how much time do I have left? Am I done? 1 minute? Okay. So this also explains Wigner's friend, right? So the puzzle here is that when Wigner's friend is inside, like the Schrodinger's cat box, never experiences any superposition, always experiences objects as located somewhere within the room, but to observers outside of the room, quantum mechanics says everything in the room is in a superposition. The P2P explanation explains this. Any game within their point of view is always going to be rendered. So Wigner's friend's perspective will be rendered. The particle will be located somewhere. But to anybody outside the room, because they're getting information but from other nodes, is always going to represent what's going on inside the box as being in a superposition. Okay. So, come to the big thing, right? People said, do we live in a simulation? And some people have said, well, if we saw any glitches in the matrix, then we would have reason to believe that we live in a simulation. Now, if this is correct, then quantum mechanics just are the glitches in the matrix that we have been looking for. Peer-to-peer networking for believable video game engines may be the deep explanation of what quantum mechanics is, why it is, and how to understand the many worlds. Okay, and it makes some predictions possibly, but I'll stop there. Thank you.
I guess one fundamental thing we see about quantum mechanics involves complex numbers, whereas I wouldn't see any of that coming in. So it doesn't, naively, it doesn't look like that sort of structure could predict the complex numbers that we have in quantum theory.
Not sure. So if someone wants to help on that, I'd be happy to get some help.
So I have I should say firstly, as somebody interested in computer games, I've really enjoyed the presentation from that point of view.
Thank you.
On the technical point, I have some technical concerns about how this fits the quantum structure, but I have a sort of more broad methodological concern here. I mean, everything we know about computability and complexity and realistic constraints on computation, even really basic things like there's a distinction between the distinction between mathematically computable and non-computable things is realized in physically implementable computer systems. Anything about the existence of resource constraints, anything even about the existence of computers in a spatial topology, all of that information comes from empirical data in the observed world. None of it's a priori. And in this setup, X hypothesis, all of that data is internal to the simulation. So I'm just worried how we could possibly know enough about what computation is like in the substrate to put any constraints on how it plays out in the observed world.
Yeah, I mean, it doesn't seem right to me that we know those things only through experience, right? We know geometry through a priori reflection, whether it's Euclidean geometry or Riemannian geometry. Same thing with computability. Now, of course, the empirical world constrains what is in fact feasible in terms of computability, right? And so in this particular reality, in ours, we're not going to be able to create a simulation as powerful as the one that we're experiencing ourselves because it has less information. We have less information to work with, right? So of course, in terms of what's feasible, in terms of implementing any particular simulation is going to be an a posteriori issue. But in terms of like the a priori features of computability, we can understand that mathematically alone.
But it's not difficult to write down laws of physics in which you could build machines that compute non-computable functions. And it's not difficult to write down geometries that aren't even faintly Euclidean, where each point is the same distance from each other point.
Sure. So
So if the universe was like that at the substrate level, then our constraints on computation wouldn't look anything like what the actual substrate constraints would look like.
sure, I don't see the problem though, right? Because what we're doing is extrapolating from what is feasible in our world to understand what is likely going on in terms of explaining at a higher dimensional level what is occurring here.
But if this is simulated, presumably what's going on in our world is entirely controllable in simulation. It's perfectly possible in our world to simulate physics that looks radically dissimilar from up to our world. There's no, so that being the case, the inference from this is what physics looks like in our simulated world to this is what physics looks like at the substrate level just doesn't look viable.
Yeah, I don't see why that follows, right? I mean, of course, we can simulate, in a dedicated server simulation, all objects having determinate locations and having nothing like the physics of our world. My claim is that in programming simulations that we know how to do, within the feasibility constraints that we have in our reality, we can explain the fundamental features of quantum mechanics in this reality, right? So I don't quite see what the problem is supposed to be.
I've iterated several times already. There were probably others in the queue, so I'll stop.
Okay. I have a comment, first of all, or two. One is that it doesn't seem to be the many worlds theory that you're talking about, but rather Feynman's path integrals, which is sort of primitive. One might easily think is on many worlds, but it isn't. Because you just say it's a sort of sum of different paths from the different computers. And then I have a related comment which confused, where I'm even more confused.
Yep.
And there seems to be some contextuality in what you say, because things get rendered when I look at it. That seems to me like a contextuality. And I'm sort of confused by having contextuality and Feynman path integral at the same time.
Okay, so a few things. So you said, where are the many worlds in this analysis? Well, every particular game is representing the world to its user as a distinct reality, right? And so there are, in essence, many parallel worlds in a peer-to-peer simulation that are communicating with one another, right? Now, part of I've got a longer version of this paper, and I argue that it actually coheres with multiple interpretations of quantum mechanics, right? In that, in a sense, for example, there are hidden variables in a peer-to-peer simulation about how the program is computing the likely paths of objects. Akin to the Copenhagen interpretation, the peer-to-peer analysis holds that all objects are simultaneously in superposition, but always collapse to a particular point when observed. I'm sorry. So can you remind me the last part of you were asking about the Feynman path integral.
Contextuality in your talk.
Yeah.
That seems to be, and I don't really understand
Sure.
how that come in. What's the mechanism that creates contextuality?
Yeah, so the mechanism is the exchange of information via dead reckoning equations to represent which particular path will be represented on this particular computer when rendered. And that's not going to be contextually the same as the path represented on another computer when rendered there.
I can understand it in the computer world,
Sure.
but I can't understand it in the physics world.
Yet I'm not quite sure what the question is.
Do you claim that everything is just a computer simulation? Then I understand it.
Yes.
Let's thank our speaker again.
Thank you.